There's those ones. Pause the video. Pause the video. If you need to see more. Here we go. Next one. Okay. Questions, comments, concerns on any of these. Anything anyone here would like me to do. Okay, so it's nice and easy. Okay, then the last one looks like this. This one gives you DV graphs, DT and DT graphs, but the DT graphs are curved. So again, unless we assume const today, not doable. Diego, what fictional universe would you like to live in? What fictional universe would you like to live in? Okay. Are there any comments, questions, concerns about anything I've done there? Going once, twice, thrice. Okay. And then questions continue. There's a lot of practice on this stuff. Those are my values. Acceleration is half a meter per second squared between 2 and 5 seconds. That's what I got. Anyway. Displacement of 6 on the bottom. No acceleration for 5 seconds and zero total displacement. Questions, comments on any of those? Why they are the way they are. Okay. These two look like this. Questions, concerns, that. Going once, twice, thrice. Sold. Okay, cool. And then there's this guy. Those the values I got. I don't actually finish this one. So that's going to be negative 2 meters. Negative 4 plus 1. Anybody want me to explain any of what I've done there? I don't know which one you're popping or bottom one. Okay. Which part? Describing the motion or the total displacement or all of it? Okay. So to find displacement on a VT graph, you want to find the area between the line and the x-axis. So for this one, we're adding this area, and that area together. So I broke it up into 3 chunks. A big triangle, a little triangle, and then that square. This triangle, again, below the x-axis is negative, and above the x-axis is positive. Because I mean, you use the numbers here. The base of this triangle, I guess, is negative 2. I just pulled my negative up front. The height is 1, 2, 3, 4. So half negative 2 times 4, or negative 1/2 times 2 times 4. Is that triangle? This triangle again, half base times above. So that height is positive. It's going to be 1/2 2 times 1. And the square here is going to be 1 times 1. I add these three areas together to get my total displacement. So the half and the 2 are gonna cancel each other. So this is going to be negative 4 here. Plus 1, plus 1, plus 1, plus 1, negative 2, negative 2. Does that make sense, Ryan? And then the last one was a lot easier because triangles are the same. One's above, one's below, one's are identical, but they're identical otherwise. So I was able to wipe those out and just find these two areas. That triangle there. And this square here. And that's that. Okay. Then I gave you interpreting graphs. Things got gnarly there. So I've got key to this. If you want me to explain any of them, I'm happy to do that. If you didn't do it, shame on lots of time. Okay, those are my first 6 questions. Comments, questions on any of those. Happy to demonstrate any of them. Yes, Diego. Yes, I can do number 4. Okay, so number 4 gives us a DT graph that has a slope straight line and a flat straight line. So on a DT graph, the slope is equal to the V. So this is a constant slope. So the V is going to be whatever it is going to be because it's up to the right. It's going to be positive, and it's the same the whole time. Means I have a constant V here. So this is constant V not equal to 0. It's something positive. And this being flat means that for this whole chunk, my velocity has to be equal to 0. So I'm going to have a constant velocity till the dotted line, and then a zero velocity till the end of the problem. Does that make sense? Rest of these like that. Okay, flipping to here's 7 to 12. Comments, concerns on any of those. Anything there? Anyone would like to discuss, explain, do from scratch. Any of those things. Once, twice. Even if you were away, it was no idea what was going on from now. I'm happy to do some explaining with a few of you who were away yesterday. Okay. Hearing nothing. 13 to 18. They get more interesting because this is where the graphs show up. So I'll just show you them three at a time. Those are the first three. I should show you my other. No. Questions, comments on any of those three. Yeah, 15 is terrible. the way I drew it isn't pretty. But let's talk about it. Okay. So here it is. We've got an accelerating object. Up to this point, it maintains some constant V. And then the velocity decreases down to 0. But in each piece of these, the velocities are all positive. Everything's above the x-axis. So we're going to on our displacement graph, we're going to have an object that's constantly moving up or this way, whatever the positive direction is. So if it's angled or sloped, non-zero slope on a velocity graph, on the DT graph, it's going to be curved. So it's going to be curved up like this. You're going to have here when it hits a constant velocity. We're going to have a straight line sloped like that. And then draw a dotted line. I like to make my life a little easier. This last little bit is gonna curve up. It was gonna curve up and be flat at that point, which is really hard to actually see what I've done there. So it's curved up. It's straight, and then it curves to flat. And then when I drew it, I actually extended the flatness just to emphasize that this did curve up to zero. But that's how you do a question like 15. And then the acceleration one's not terrible. These non-zero slopes are where this thing's accelerating. This is a zero slope, so there is no acceleration. The velocity is constant. So we're gonna have something like this, like that, and like that. And this one has to be further down than this one is up because this one is steeper than that one. We don't know what the values are, but we do know that this one is more negative than this one is positive. Does that make sense? Yeah. And then 16 to 18 look like this. Is there anything in there anyone wants me to do? Sorry, is that a hand? No. Okay. Going once, twice, thrice. Sold. There's another page. Keep going. These ones look like this. We can actually play with some values on here. I technically the third one that gave us values. Nope, we have values for all of them. And so we're actually able to plot some values on these graphs. So if this one is 56 up and 8 over, rise over run, 56 over 8 is 7. So that means a constant velocity up 7, no acceleration here day, good morning. You could live in a fictional universe you want to live in. Okay. Sorry. Okay. This one, given these values, if it's constantly accelerating at 5 meters per second, 4 seconds, that means after 4 seconds, moving at 20 meters per second. If it starts at zero, I have a curved line looks like that. For this one, constant V, it's going to look like this, and no acceleration. And then these bottom three. Are going to look something like that. Comments, questions, concerns on any of those. Yes. I can do 24. Okay. So we've got a okay. We've got zero velocity to start, and it increases to some maximum.
and then it slows down and reaches zero. But all of that's positive. I'm going to ignore the values for now. What a zero velocity up to some maximum velocity looks like on a displacement graph is something like this. It's going to be curved up because the displacement is going to get larger as the slope on this is going to get steeper as the time increases. We're still going to be moving positively here, but now it's going to start to curve down because our vol is approaching zero. So this thing needs to go up and over, something like that. At this peak is when this thing flattens off, and we're going to get exactly the mirror image. It's going to start to speed up negatively, reach some maximum negative, and then slow down to a stop again. So it's going to start to speed up again, and then it's going to start to taper off, and flatten off at the end. The only thing we could do, for each of these pieces, we would know what these displacements are. We calculate those by area under the curve here. So that area is going to be 10. So this would be 10. This guy's also going to be 10. So this would be 20. This would be negative 10, which brings us from 20 back down to 10. And then this would be another 10, bring us back down to zero. So we can use those values there. We can also use these values to find ourselves the accelerations. The slope here is 4 over 5. So that's going to be for the first chunk. It's going to have an acceleration of 0.8. And then this whole chunk is going to be the same. It goes down 4 over 5, down 4 over 5. So that's going to be a rise of negative 0.8. And then this slope is the same as the first one was. Back up at 0.8. And that's it. Comments, questions, any of those things. Yeah. 22. 22. 22. 22 if I've got a velocity graph like this. This is accelerating from 0 up to 10 over 4 seconds. So I can actually do the calculation here. It's going to be the area there is going to be 10 times 4 divided by 2, 20. So I'm going to have maximum displacement here. I'll call that 20. And because velocity starts at 0 and reaches some maximum, it's going to curve up. And then it's going to reach some flat velocity, which means that's a constant velocity, zero velocity. Constant velocity means that we're going to have a straight line on our DT graph, and that straight line needs to go up to that is 5, that is 10, so that's going to be 50. We're getting displaced in this pink chunk another 50. So 20 plus the 50, we're actually going to be somewhere at 70. So there, I need to be over at 70. It's going to be a straight line. So it speeds up and goes straight. And then our the acceleration is going to be the slope of this line. So that's going to be a rise over run. 10 over 4 is 2.5. And that's a flat line. So that's a zero acceleration. Something like that. Here it is. Let me see. Okay. Common questions, any part of that stuff. Going once.
twice, thrice, soul. Okay, cool. Yay, we've only got pep rally today, so I've got short block, 35 minutes left. I want you. You know what? Keep saying start of this, and we'll come back to this. We will come back to this, but not now. Will be part of review. I'm just gonna pull this plug on this page. It's a fool's errand. We'll come back to this part of your guys' chapter review. I've made you graph enough for the time being that have no meaning. Now I'm going to give you some meaningful graphs to do. Find me this page. Acceleration due to gravity. Okay, so we built up to this point. We talked about how things are, how they move. We talked about velocities, both constant and now accelerating. The one major acceleration we haven't talked about yet is the acceleration due to gravity. Drop an object, it's going to start to speed up towards the ground. Or if you have the misfortune of being under something that gets dropped on you, it's speed up towards you. And we're going to figure out how that happens. What that value is for the acceleration due to gravity is the lab that you're going to do for me over the next couple of days. So we're going to start this here, and you're actually going to start this lab today. So the acceleration due to gravity.
I got a couple objects here. Drop some stuff. This guy here. And this guy here. Really similar. Use this guy. Okay. More massive. How do you know? This would be really lead. Put in the bag, more massive. No, so she was right. So I've got two objects here. Perhaps you see this in the sake of one round. Do it again. I'm gonna drop both of these objects. Which one's gonna hit the ground first? The book. Hands up for the book. The book will hit first. Hands up for the bag of coffee. Bag of we believe me. Or if you believe Alexis, bag of coffee. Hold that. Be nice and line. Hold this. But that's how we drop it. How do you figure? So you tell me how to drop it. I'll drop it as many times as you want me to drop it. Let me do this. Okay, here we go. Which one hit first? Bang. Again. Be same again, right? It really matter. Same. Cool. Do one more time. I'm use that piece of paper. Because this is what you're thinking, right? This one has. This one's lighter. So this one should hit the ground second. And perhaps some difference here. Why that is? Because this one was definitely lighter, but they hit the ground at the same time, right? So if I do this, you know the paper is gonna do what? Presumably it's gonna do this. Float down. Okay. So what's going on there? What is the significance here? Yeah. Okay, so because it's air resistance. Careful. Because it's air resistance against the gravity. Gravity acts the same way. This one also has lower mass. And they hit the ground exactly. So where's the tipping point there? You're right to say air resistance is the issue. I'm not going to attach these to each other. A little bit lighter. Smaller piece of paper, which actually makes it less air resistant. That's okay. With all of the air resistance, I'm not
to attach to each other. I'm just going to place this one on top of the book. Now when I drop it, what's going to happen? What do you think is going to happen? You can still go float. How many of you agree with this? Is it going to float or not? Is it going to float? We just don't know what to think anymore. I was going to say, we remove the air resistance. Air resistance no longer becomes an issue. When I think it's not attached. Like there's nothing sticking to paper to this. I can just drop it. I do it on the desk. Those are easy to like it hugs the paper all the way down. So the book cleared out all those air molecules. So something about air resistance is really impact. We're not going to. In fact, we're not going to talk about it in high school at all. We'll talk about that it exists, but the math behind air is wild. So this thing, you also have different errors, right? They're shaped different off these like this. Those same time. So air resistance becomes dicey. If we remove air resistance, right? Like here. Hoping I managed to do that. These two objects fell at the same rate. Not because they were attached. Not because the book was stuck along with it. But because it doesn't actually matter what your mass is. If I took who's the smallest person, Diego or Alexis, and I probably the most person here, all jumped off the building together. We would hit the ground at the same time. It doesn't matter what your mass is. The mass of the falling object doesn't matter. The only thing that matters. And actually, there's a video I have of a ball and a feather. The classic example of those two things. And they drop them once, and then they back and drop them. It doesn't matter. But the mass of the object being dropped is. The only thing that matters is the mass of the object. Sorry? No. I shouldn't drop what? Oh, I shouldn't jump from there? There's always a time and a place to jump from a building. There's always a reason. You can contrive something. Maybe not this building. Acceleration due to gravity. Acceleration due to gravity. This value whatever it is does not depend on the mass of the falling object. Ignoring air resistance. Because that's where we get things get dicey, right? We think about planes and parachuters. We see two people jump out of a plane, and one person catches the other person. Well, how does that happen? If gravity's acting on them both equally. Yeah, you're changing your. Maybe one of them is diving out of the plane as opposed to flat. They're changing how the air is interacting with them, but remove air, which I know is hard to do on this planet. The mass doesn't matter. So the acceleration due to gravity does not depend on the mass of the falling object. Only the mass of the object creating the gravity. Which we're going to look at in more detail in a subsequent chapter. So acceleration due to gravity does not depend on the mass of the falling object, only on the mass of the object creating the gravity. So Earth has a value for the acceleration due to gravity. The moon has a different value for the acceleration due to gravity. The sun has a different value for the acceleration due to gravity. You have a value for an acceleration due to gravity because you have mass. Objects are gravitationally attracted to you. Though you don't experience it on this planet because you've got a nearby object that creates a whole lot more gravity than you do. The Earth.
But you can calculate the gravitational attraction
you and anyone else in the room.
In fact, it's an age-old physics pickup joke or pickup line. Because any two objects that have mass have a gravitational attraction. Maybe not different, any other kind of attraction, but gravitational certainly. So what happens when you toss an object into the air? You throw the ball up.
Always a ball, always a ring.
No, I have a ball. What happens?
All done before. It goes up, back down. Cool. Can you be more specific? The softball. Just gonna leave my hand at some velocity. It's gonna eventually stop. It's gonna come back down. Lots of throwing. Yeah, do it. And what can you say? What can you say? What's my up? Go up and take the time to come back down. What is it? Here to you. Sorry. How long did it stop for? 0.1 seconds. You stop watch. So again, I want you to time take the whole thing that occur. The whole thing, up and in there. Okay, so 1.15 seconds. You stop for one of those. Point something. But very small amount of time. For an instant, argue what I was saying. For an instant, the thing stops back down. Okay. I want to try this. Sorry. I was on what time feel up is, and you're timing when you feel back down. You think it starts to fall, and you're gonna decide. Use my hand and stop it when it gets to the top. You're gonna start when you get to the top. You're gonna stop when it put down. What's your time up? 0.8, down. So you got one, you got 8, let's do it again. Now you've done it, let's do it again. Again. 0.5. So within error, after you go back to the reaction times, reaction 1 seconds. You can combine your errors. And what I'm trying to get is that yes, there's gonna be time where the thing slows up to a stop, hangs there. But as far as the time up and time down, they're effectively what can I do with bigger time? One more start. Here we go. Ready? That's again. Over. Reset. And not in the ceiling. In between those two. Here we go. What do you get? I think you made. Oh, seriously? You got here because let's try again. Because you got a last 0.7 seconds combined. And before Simran got one in the middle second. That's right. Not hit the ceiling. Yeah. I'm up. 26. Come on, you're dead. That's 22 seconds. That's hard. Difficult to do. I hope by demonstrating this and not quite working out, I screwed it all up.
What we've got. I threw the softball in the air a whole bunch of times. Got a softball there. The thing rises. It has some initial V. When it leaves my hand, whatever that value is, it's non-zero. VI there is positive, which causes this thing to rise. The ball goes up. And the whole time it's rising. It has to be slowing down because Simran said and then noticed and then it was true. The ball does stop there for an instant and then begins to fall back the other way. So this whole time we have to be slowing down. And then the ball's going to turn around and fall back down. At this moment, whatever it is, V is equal to 0.
for an instant. And then it starts to fall. It starts to speed up, down. What I tried to convince you of, I don't know if I did a very good job of it, is that the time it takes go from there to there, that time, whatever it is the same amount of time it would take to fall down. Those two times should be equal. And if those two times are equal, that tells us a few things. Obviously the distance up and back to the level is going to be the same. The time up and down is going to be the same. If the acceleration on the way up causes particular time to be whatever it is, 0.6 or whatever Cyril measured it to be. And here they measured it on the way back down. They should have been basically the same. What that means is for all of this, A is constantly downwards the whole time. And is constant. The value for gravity doesn't change during that flight. Now, if you go to different places on our planet, the value for gravity is different. It depends on the shape of the Earth beneath you, the distance from the Earth. What that ground is made of is different portions of our Earth have different masses because there's a higher density. If you're standing on a big deposit of lead, for example, versus a big deposit of topsoil, it might be the same distance from the center of the Earth. The mass over the lead is larger than the mass beneath you over the topsoil. So there are different values for A at different points on the Earth, which is weird. But as far as an isolated rose back down, A's constant the whole time, and is down always. Where students often get confused, we had to accelerate it up. What was doing the example when I had the ball and I was throwing, what was causing this thing to accelerate up? How did we give it an initial velocity? What caused the object to be moving up to begin with? Me. So I gave it an upwards acceleration. Left my hand, but as soon as it leaves my hand, I'm no longer acting on it. So as soon as it leaves my hand, only acceleration acting on is the acceleration. Interestingly enough, V final. Yeah, it's going to be negative. The object's coming back down towards the ground. So the directions are different. But for objects that are level, these two velocities, the magnitude of those velocities is actually going to be the same. Those are equal. This one's up. This one's down. But this object hit my hand at the same speed that this one left my hand. What happens if you toss the ball on the moon? You guys seen footage? It would take longer to do the exact same thing because the moon is less massive. Okay. So what would happen if you toss on the moon? It would take longer. And if it's taking longer, what else is probably going to be true? For the same initial V. If I threw it up the exact same way I just did here on the moon, what else would be different? Nope. Because if I was at the beginning, if I managed, if I'm on the moon and I managed to throw it up the exact same way I did here in class. It would take longer, and one other thing is true. If it's taking longer to do the whole path, it's taking longer to slow down. If it takes longer to slow down, what's that going to tell you about the path? Hear it. It's still these two times are still going to be equal. But what can you tell me about the path? The displacement, as it were.
it would rise higher. It would take longer. Rise higher. Should be a word and in here. Those are the only two things. It would take longer and rise higher. Because there's less gravity. And we'll get into those values in a little bit. Because this is the explaining. It has less mass. The moon is less massive than the Earth. Okay. So I am going to in the next 12 or so minutes, you guys are gonna start to prep for your lab tomorrow. Here's what you guys are gonna do. Introduce the equipment, and you're gonna prep your object for tomorrow. That'll be this thing here is called a spark timer. You plug it in, you turn it on. You're gonna leave it set to 60 hertz. I don't know if you see it from where you're sitting, so I'll zoom in on it with my document camera. Inside this object, there are two copper strips. Can you see? What is that? Air. There's two copper strips inside, and they are separated by some distance. When you turn this thing on, nothing happens until you give them a way to connect. This silver paper here is called spark tape. And spark tape is conductive on one side. You can see if I take this off here, I'll rip that first bit off. And it's starting to unravel like crazy. On one side of the spark tape, maybe I can see the difference here. That's white. Flip it over. Oh, it's shiny. I'll do it this way. This is a matte finish. Backside, you got conductive. Matte finish. White, conductive. You got something conductive going through something that requires a conductor. So when you feed this thing through here, the spark tape, you can see as it hits the end here, what this is going to do, these two copper strips and this paper. The paper is going to allow electricity to flow between these two copper ends, and this thing is going to make burn marks on the paper. You're going to create an object today in the next 10 minutes that's going to pull the spark tape through the spark timer from a height greater than 2 meters. I've got some objects here. I've got golf balls, bouncy balls, solid wooden blocks. What I want you to do, a partner or a group of 3, is to grab a subject, and I want you to create an object that has a mass between 100 and 500 grams. The only object currently that is this softball. It is 200 grams. But everything else is too light. So you're gonna take from here. How you do it? Combination you choose. Here's the scale. Now I'm gonna give you a bunch of masking tape. And I want you to create some object that has that mass. Somewhere between 1 and 500 grams. Ideally, I like different than your other groups, so that we can show that different mass objects are actually going to all accelerate the same way. Once you create your object, I want you to write your name on that object back in that bin, so that you can find it again tomorrow.
We're gonna drop these objects attached to spark timer. Attached to spark tape through the spark timer. You guys are gonna see much bigger of these graph. So now it's only Go. In twos or threes, that object. The scale is there and on, test it. And then you have to write your name on the tape. Someone already has blocks together. No one else takes 2 blocks together. All your objects need to be different. Also, I want you to write what the mass of that object is. Because you're going to need to record that as part of your lab. You just took the softball. Okay. Yeah, the mass on there as well. You just survive. Survive. Yeah. Like that's Gotcha. How destroys them? You yourself. Yeah, throw in a device and use whales on it.
we're year 3. You just have to do it for year 2. You're not doing that. No, you're gonna hate me. Just smash. Why is he well, it's just That's the way the liver works. Oh yeah, it's fun. Okay, so until the bell goes, I'm gonna hand this up today because I want you to lose it, but I'm gonna go through the lab handout while you guys are working. You guys are going to use the spark timer that I showed you, the tape I showed you, and the objects you just created to find the acceleration due to gravity in the groups that you just made. So what you're going to have to do is drop that object attached to some spark tape from a height greater than 2 meters. Now those spark tape or spark timers require a source of power. So you're going to have to find an outlet. And I'm not going to restrict you to staying in this room. You can work out there on the couches. You can find a place down the hallway where you've got an outlet high enough to drop from a height of greater than 2 meters. Sorry? No. Because I'm only going to give you 2 meters worth of tape. So you don't need to drop it from higher than 2 meters. We'll drop something from the rotunda later. The energy, the bungee lab I told you about. You guys are gonna drop eggs. It's gonna be great. So when you drop your object attached to the spark tape, the spark timer is gonna make a bunch of dots. And these dots are gonna start spaced close together. And space Simran and Syra are gonna get spaced further apart as the object falls because as you guys should probably guess, that object is going to start to speed up. What you guys are going to do once you drop the never mind. We'll talk about it tomorrow. The object needs to stay back in that bin. Have a great day. Enjoy pep rally. See you tomorrow. Sorry. Yeah, if you want to go, you're welcome to do that. Do it. Weird objects. I love it. This is yours. This is yours. I love it. 3 blocks. This thing. How are you today? Better? Have you eaten it?
The swelling's gone down a bit, but still.
Yes. Well, yeah. Have you eaten anything solid yet? Probably wise. Did they give you any fun medications? Not that you know it? Okay. I had my wisdom teeth pulled